Okay, so today we're looking at another interesting problem called kth largest element in an array. Essentially, we're given a nums array and an integer k, and we're told to find the kth largest element inside that array. So taking a look at example 1 here, we have the following nums array, and we're told to find the second largest element. It's pretty easy to tell that the return value should be the number 5 here, as it's the second largest element inside this array. One example I want to highlight is the following. We can also have a nums array like the following with a k equal to 2. In this case, I would expect you to return number 3 as the correct answer, not the number 2, because if you look at the directions, it says the kth largest element is not a distinct kth element. Finally, I know that the problem statement just says just try to solve this in O of n time complexity, but let's just ignore this constraint for now and explore some interesting approaches. Okay, let's just get the easiest approach out of the way first. Essentially, this one just requires us to sort the array. Should be the first one that comes to your mind because this is the brute force approach. If you take the following array and you sort it, you get the following. Now, using k, we can use indexing to retrieve the output in O of 1 time. So in Python, you can use negative indexes. So I will take index -4 or negative k and return this. To evaluate the time complexity for this solution, pretty simple. Assuming we use an optimal sorting algorithm like merge sort, it should be n log n, and no extra space was used, so O of 1. So to do it on leetcode, pretty simple. We're going to take the nums arrays that's passed into us and sort it, and then we can just return nums at -k. Simple and really effective. Okay, so in our last solution, we really made use of sorting, but maybe we don't need to sort the entire nums array. What we should think of now is some data structures we can use to optimize the time complexity. One that should come to your mind is the heap. And actually, for this example, we're going to be working with the max heap, and you'll see why in the simulation. If we take this nums array and we heapify it, we should get something like the following. As you can see, the heap isn't totally sorted, but at the very least, we can guarantee that the element at the top of the heap is in the correct position. And that's really all we need to solve this problem. What we're going to do is we're going to pop from the heap k times, or actually k minus 1 times, so that the element that's the kth largest is still within the heap. And at each time we do this pop, this is a log n operation because every time we pop from the heap, it needs to rebalance so that the correct element is at the top of the heap. So let's run through a simulation. Right now, k is equal to 4. We're going to pop from the heap, so the 6 is gone, and the 5 moves up. The 5 is in the right position. The k has been decremented down to 3. We're going to pop from the heap again. The 5 is gone. Now these two switch places, so let me fix that. We pop from the heap again, decrement our counter, and finally now the counter is down to 1, and we don't need to pop from the heap anymore because our answer is at the top of the heap. Let me clean this up. So before we evaluate the time complexity, we have to touch on the heapify we did to build the initial heap. Heapify is really an O of n operation because it's able to build a heap using a sift down where all the nums elements are given to it, and so it's able to do this in O of n time. Whereas had it built the heap using a sift up nature, it would have been n log n like a merge sort algorithm. But regardless of this, the overall time complexity for the solution would be k log n, k because we do k pops, and log n because the size of our heap was the total nums array. And because that was the size of our heap, our space complexity is also O of n. Okay, let's do this on leetcode. So the first thing we need to do is create our max heap. Python does not have max heaps, but we can still achieve it by inverting all the values in nums like so. Once they're inverted, we can use the heapify function. Okay, now following our example, we're gonna pop from the heap k times or k minus 1 times. So the element we want to return remains at the top of the heap. Let's pop from the heap. So heap pop. Every time it pops, that's a login operation and it will rebalance. Then we can return the value at the top of the heap. Make sure you re-invert it before you return it. Forgot to do decrement. Here we go. Time complexity, pretty simple. Just to note again, the heapify is an O of n. The heap pop is a O of log n. And we do this O of k. Hence, it's k log n with the space complexity of O of n. Okay, so far we've only focused on improving the time complexity. This time I want to see if you can solve this problem with an improved space complexity. So here we're actually going to be using the heap again, but with a slight difference. This time we're going to be working with the min heap. So just to recall, the goal of this one is to improve the space complexity. So look what happens if we create a heap again, but this time of size k. Now, given that we have a heap of size k, which is a min heap, we're going to go through the nums array again. We're going to do one pass through it, and each time we go through it, we're going to put the value into the heap. At each time we put the value into the heap, we're going to check the size of the heap as well. So it'll make more sense if we run through this example. So we come across the 3 and we push it onto our heap, and it comes over here. We check if the size of the heap is now greater than k. It's not, so it's cool. We can continue adding more values. Now we come across the 2, we're going to push it onto the heap. Now because it's a min heap, the smaller values are going to get moved up to the front while the larger values remain at the bottom. This is one of the reasons why we're working with the min heap, because we want the larger values to remain in the heap. Same thing happens next. We're on the 3, we push it onto our min heap. Come across the 1, we push onto our min heap, it rebalances everything. Now look what happens when we come across this 2. We're going to try to push it onto our heap. We're going to push onto our heap, but we're going to realize that the heap is now larger than size k. In this case, we're going to have to pop from the heap as well. What happens is we push the 2 onto the heap. It comes somewhere around here. And now the 1 needs to pop off. And now you can see why the min heap is really important here and the differentiator, because now all the larger values remain inside the heap while the smaller values get popped off. So let's work our way through the remaining array. Push the 4 into the heap, it comes over here, the 2 gets popped off. Push the 5 into the heap, the 2 gets popped off. We push the next 5 into the heap, 3 gets popped off, and finally we're at the 6. Push it into the heap, and the 3 gets popped off. So now our heap looks something like this at the end. And as you can see, the 4th largest element is at the top of the heap, where it should be. So let's evaluate the time complexity and space complexity of this solution. Now, because we did go through the entire nums array, and at each point we did have to push these values on top of the heap, that is an n log n operation. And because we went through the entire pass of nums, n log n because each push operation is a log n operation. But now look at what happened to the space complexity. In the last solution, the heap was the size of the nums array. However, this time, because we chose a min heap, the size of the heap is only O of k. And actually, let me clarify this. This should actually be log k because the rebalancing is happening on the heap, which is of size k, not log n. Okay, on leetcode, let's create our heap real quick. It's going to stay empty to start off with, and we're going to go through all the values in nums. So for n in nums, first thing we're going to do is we're going to push the element into our heap, so heap push. After pushing, we need to check if the size of the heap is greater than k. If this is the case, then we need to pop the top element off the heap. And finally, with that, the kth largest element should be at the top of the heap. Okay, and I hope the time complexity makes sense. Log k, because this heap push is a log k operation, so is the heap pop, but we go through the entire nums array. And that's also why the space complexity is O of k. So there is one last solution to this problem. So far, all the solutions we've looked at can do it in k log n, but there actually exists one more solution that can do this in O of n time, and it uses a algorithm known as quick select. This can do it in O of n time. So better than all the solutions we looked at, but it's one I won't be covering because there's already solutions available on YouTube. But I will leave you guys with a follow-up question. In this problem, we looked at how to find the kth largest element. How about I tell you guys to find the kth smallest element? So a pretty simple alternation of the problem, but I really want you guys to see how your choice of heap, min heap versus max heap changes now that I'm asking you a slightly altered question. Best of luck.